Hello everybody, my name is Robert Brotzman, and I'm happy to be here to share with you our work SpecSafe, Detecting Cache Side Channels in a Speculative World. To begin, I first want to go over what a side channel attack is. A side channel attack is typically defined as the unintentional revelation of some information via an observable characteristic about how the data is being processed. A common use case for side channel attacks is to extract cryptographic keys. This is often the case because cryptographic keys tend to be small, usually at most a few thousand bits, and are significant once an adversary can uncover them because they're able to use it to identify both past and future communications from victims. Now in this example, we have a plain text and a key. It's going to be processed by a machine that's going to give off some information and produce a ciphertext. Now, side channel attacks have been demonstrated by observing the power of a computer, even the electromagnetic field of a computer as it's processing some data. These require physical access to the machine. And more troublesome are attacks that can be launched remotely. These can be done by observing the execution time of a program or by observing the state of the CPU cache as the program executes. What the adversary will do is they will send usually multiple plaintexts with the same key, and what they want to do is get a strong signal by correlating the key with some expectation, and as they get more information, typically the correlation will become stronger and they will get a signal of what the key is. Now that we have a high-level understanding of how side channels work, now we'll take a look at how speculative execution works. We first need to understand that CPUs execute sequences of instructions, and the sequence of instructions is going to be dictated by the programmer. Sometimes the CPU will guess what to do next in order to save time. So for example, when it encounters a jump instruction, it may not immediately know which path needs to be taken for multiple reasons. When it does this, we call this speculative execution. And the reason we do this is that if it guesses correct, we save time because the processor would essentially do nothing while it waits for the condition to be known so it knows which branch to take. On the other hand, if we guess wrong, we discard the work that we did speculatively and we do the work that we had to do anyway. The key thing to note is that on a misspeculation, we have to roll back the architectural state. However, we maintain the microarchitectural state, such as the state of the CPU cache. So what can go wrong with speculative execution? So here we have a simple example. It's just a program that has a condition here on line 4. And based off that condition, we have two array accesses. We'll access array A and array 2. So now when the processor gets to line 4, when we execute this if condition, it'll be lowered to some kind of jump instruction, most likely, some conditional jump. The processor will ask the branch predictor, where should it resume execution? So the branch predictor will guess either line 5 or line 8. And the processor will then begin executing at that point. And now an important thing to notice here is that this is regardless of whether this condition is true or false. So if we guess that we are supposed to execute line 6, and it is the case that x is actually greater than a sub, the size of a, we could inadvertently access out of bounds memory here, a sub x. So if x is controlled by the attacker, they may know where the key resides in memory, ask that the processor loads that here, and then that would be encoded into the memory access of array sub 2 here. And this can be extracted using conventional cache side channels to infer what offset in array sub 2 was used. And that offset here would be 2, which corresponds to the value of key that the adversary is trying to uncover. Now that we have explored how speculative execution can be leveraged to create cache-based side channels, now we'll take a look at existing work that seeks to identify cache-based leakage in programs. There's been a lot of work done to identify conventional cache side channels in the literature. One such work is cache audit, which uses abstract interpretation in order to identify an upper bound on how much leakage can occur in a program. More recently, we've seen with cached and CASM the use of symbolic execution to pinpoint in a program where the leakage is occurring. More recently, with the advent of Spectre, there's been a lot of work done to identify these leaks in programs. These works such as Spectre, Teapot, and 007, however, pretty much exclusively focus on code that is speculatively executed while not considering leakage that occurs during non-speculative execution. Our observation is that these approaches may miss interesting side channels, and our proposed solution is to consider both speculative and non-speculative program traces simultaneously. During our work, we discovered 3 unique code patterns that have previously not been identified in prior work and are seemingly not detectable by existing techniques. One such code pattern is presented here. In this example, we have a conditional that will access A if key is 0 or not access A if it is not equal to 0. So at some point later, we will then use A in another condition. And the thing to note here is recall that if A is cached, it's unlikely the processor will speculatively execute. However, if it's uncached, it is very likely the processor will speculatively execute one of these branches. Now what we know is that if a misprediction happens, we should expect to observe both B and C in the cache, so an adversary can observe those memory locations, and if they observe that both of them are present, it indicates that a misspeculation happened. And what this tells the adversary is that A is uncached, which means it was not accessed here, which leaks information about the key. We crafted covert channels for each one of these 3 code patterns that we identified, and we were able to generate up to 65 kilobits of leakage using these new code patterns. The key observation here is that whether or not speculative execution happens can actually leak data and has, as far as we can tell, been overlooked by existing work. Now that we have seen a code pattern that is not identifiable by existing techniques, we'll take a look at a policy that can identify the leakage that we observed in those code patterns. So existing notions may misidentify the new leakage patterns because they either only are looking at conventional cache side channels, which do not consider speculative execution, or they are exclusively looking only at the speculatively executed parts of the program traces. Neither of these can identify that there can be leakage based only on the fact that speculative execution happens or not. We propose SANI, or Speculative-Aware noninterference, and the idea is that we can capture this new speculative leakage by considering all execution traces, both non-speculative and speculative. Now we'll take a look at how we can capture speculative execution. We propose doing this using program transformation, and we do this by rewriting the program to include the additional code that will be executed during speculative execution. This allows us to reuse symbolic execution engines such as CASM that are cache aware. In order to create this program transformation, we need to introduce 2 new commands, one for capturing the current architectural state, and the other to roll back the architectural state during a speculation. The capture command will record the architectural state and assign it to some ID. And the ID is going to be important when we have to roll back to the architectural state, so we then know the architectural state that we need to get back to. And rollback will reset the architectural state to the given identifier. Now, the key thing to notice about rollback is that we will not be resetting the microarchitectural state. For example, it will not reset the CPU cache. And this is important because on actual hardware, when speculative execution is determined to be incorrect, the processor will roll back the architectural state. However, it will not roll back the microarchitectural state. And as we have seen, that is where these side channels actually manifest. Now we'll take a look at how we can apply our program transformation to a program that has a Spectre vulnerability. And here on the right, we have the transform program that we will feed to our analysis. Now to begin, we first need to introduce a capture command before we enter either of the if condition blocks. Recall that capture will save the current architectural state, but not the microarchitectural state. To begin, we will copy the else branch here, because and this simulates a misprediction. That's because when the branch prediction oracle guesses false here, this condition will be true. So the predictor guesses that we will enter this else branch here. We'll execute the code in the else branch, and then we will roll back the state. And here we're only rolling back the architectural state and maintaining any side effects that occurred to the cache state. And see here, we then would execute as normal the remainder of this block. And conversely, we have when we execute the then branch on a misspeculation simulated here, we would first execute the code from the then branch, and then we would execute the code from the else branch. And again here, recall that this is the prediction from the oracle. It guesses that we execute the then branch first. And then after we execute that code, we would roll back the architectural state, but not the microarchitectural state. Our tool would identify a problem here, and this is because a sub x is no longer guarded by this condition here. So it may be out of bounds, and it may read sensitive data from memory and load it into the cache, which is observable at this point. In the paper, we have formal proof showing both this program transformation and others, that if the transform program satisfies SANI or cache noninterference, then the original program satisfies SANI, and these proofs can be found in our paper. Now we'll take a look at how SpecSafe performed on the libgcrypt suite of ciphers. To begin, we used a quick taint analysis pass that identified 29 functions out of 346 that are going to be interesting for us to analyze with our symbolic execution. We did this because the taint analysis is much more lightweight than symbolic execution to try to run over so many functions. Of those, our symbolic execution removed 5 false positives from the taint analysis identified here that violate our SANI definition. In addition, we found 2 new potential Spectre leaks in libgcrypt, one in the cha-cha-20 cipher and another in the salsa cipher. In conclusion, we discovered 3 unique code patterns previously undetectable by state-of-the-art approaches. We developed a novel security notion to accurately capture cache leakage under multiple cache models. In addition, we proposed a program transformation to capture speculative execution, and we proved the soundness of these program transformations in our paper. Lastly, we detected a potential Spectre-style leak in libgcrypt's cha-cha-20 and salsa ciphers. That is it, and I thank everybody for listening.